Ladies and gentlemen, I would like to welcome you to this webinar on the market launch of Eyestar, our new precision OCT device. My name is Reiner Herrmann. I am the Global Head of Marketing for Haag-Streit Diagnostics. It is our great pleasure today to welcome you for this webinar and to introduce the Eyestar to you. Before we do that, I would like to give you a short overview on the program. In this program, we would like to bring the Eyestar closer to you. For that, we have designed two presentations. In a first presentation, I will give you an overview on the Eyestar and its market introduction into the global markets. Then, in a second part, and this is a major part, Thomas Beutler, our product manager for Eyestar, who was also instrumental in the design and development of the product, will give you more detailed information about the Eyestar features, the benefits, and the clinical value of the device. And then in a third part, we will be there for questions and answer, and we hope to answer all of your questions. Now, starting with my overview, I would like to show you quickly a 2.5 minutes video that describes the Eyestar and shows you the device a little bit more.
With the Eyestar 900, Haag-Streit is opening a new chapter in measuring, imaging, and diagnosing the human eye. The Eyestar 900 features all Swept Source OCT technology for precise biometry, topography, and keratometry, excellent planning and diagnosis, and detail-rich visualization. The Eyestar 900 Swept Source OCT with a patented scan pattern features type A topography of the corneal front and back surface, pachymetry maps, OCT biometry, and dual-zone precision keratometry. Accurate diagnosis with features like Zernike wavefront analysis, vision, simulation, and lens tilt analysis supports the eye care specialist to accurately plan surgical procedures and to assess outcomes. The fast and fully automated acquisition process enables easy delegation and improved patient comfort and compliance, thus ensuring excellent measurement results. iSuite IOL is an excellent graphical planning platform for cataract interventions that features a set of state-of-the-art IOL calculation methods like Hill RBF, Barrett and Olson for any IOL type or corneal condition. These features result in more accurate predictions, fewer surprises, and excellent outcomes. The pooled information with biometry, topography, and tomography enables the eye care specialist to diagnose diseases quickly and reliably, improve planning of surgical interventions, and document eye status for improved outcomes and less surprises. Topography maps up to 12 millimeters, extended Zernike wavefront and vision simulation, progression analysis, and keratoconus screening are only a few of the planned features for the anterior chamber suite. The Eyestar 900 is not only an investment in state-of-the-art technology, but also an investment in the future that will provide added value over its full lifetime.
So, the Eyestar has come quite a way, and now finally the star is born. Actually, as you might have known from the press, we have received the CE marking already by May 2020 last year. And then we did pilot installations in a number of sites in 2020 and 2021. And now in 2021, we are ready for the market introduction of this new device. The video has shown quite a number of features. I would like to give you my own words on some of the main features of this new device, and Thomas will then later on go into the details. Now, first and foremost, I think we need to start with usability. The device has an very good usability as it is fully automated. There is all movements basically are inside the device, and it is just started by a push of a button, and then the device automatically aligns, captures, and measures. It does not require any interaction of the operator, and thus provides highest patient comfort with these automated measurements. And all that is done in about 40 seconds. All acquisitions are really done, and that means all. It does not require any second or third alignment like in other devices on the market for measuring other modalities. We capture all data in one go, and then they are ready for analysis. The other main point is certainly that we have here a device based on Swept Source technology that is first and foremost designed for high precision measurement. It includes a topography that is all based on OCT data and is fully classified as a type A topographer, which means it fulfills the highest norms for topography in ophthalmology. And then with this topography, we provide a number of comprehensive maps of the front and the back surface of the cornea, as well as pachymetry maps in different variations. All these values can then instantly be used for surgical planning and for IOL calculation. So it really allows the user and the physician to screen the patient for any corneal pathology that might limit the patient's post-cataract visual potential. And that is critical, as we all know, in IOL design and planning. Then when we have this data, we move on to our Cataract suite. The Cataract suite is known from the Eyestar, and now it uses next to the known values which are provided by Eyestar, it uses the values that are provided by the Eyestar and that are more detailed, and we have more values that we use here. The Cataract suite comes with the latest IOL calculation methods, such as the Hill RBF 3.0, the Barrett, and the Olsen formula. And as you probably know, the Hill RBF is purely data-driven, and it is a calculation method based on artificial intelligence that has shown excellent outcomes in numerous studies, and it is really suited for all types of eyes, be it short, long, or normal eyes. And the Hill RBF provides also reliability features such as the boundary model, which are really unique in IOL calculation. These new IOL calculation methods use biometry data that are beyond axial lengths and K values, and the Eyestar is really the ideal device to provide these data. The aim of all this technology is to allow the physician a detailed judgment of the patient's status before surgery, to have best outcomes, and to have the least possible minimum refractive surprises. So with that features, the Eyestar is designed for a number of applications. In first and foremost, it is designed for cataract, for the cataract surgery planning, as we launch it today. It does a measurement of the biometry of the entire eye, so different structures, different compartments are precisely measured in a three-dimensional way. Then we use this data for IOL calculation with the latest formulas and the latest planning procedures. And the device also already carries corneal topography and allows to visualize the anterior segment. These latter two segments that will be extended in the future, so you will see new software coming up to allow for more visualization of the anterior segment and to an extended corneal topography. With that feature set, the Eyestar is designed for leading surgeons who appreciate the value of precision measurements and their contribution to excellent surgical outcomes. So in a sense, this new device defines a next generation of biometry for cataract surgery as well as for anterior chamber analytics. We are bringing this device to the market now, and we have a staged approach to the market. We already launched it in Switzerland, where we have a number of pilot installations. We did that from May 2020 onwards. And now we are ready for a second stage where we introduce the device to the Western European markets. And as we roll up our production, we will be ready in a third stage to serve the global markets wherever we have a registration which allows us to market the device. So this is our global approach to the various markets, and this approach is accompanied by educational measures where we introduce the device and have education about the background of the biometry that is feasible with this new device. To do that, we have designed a number of webinars in this series of webinars, called the Biometry Focus Months, where we have today the first seminar. As of May 6th, we will have more webinars by leading experts on biometry with the Eyestar. In the first webinar, Warren Hill will talk more deeply about topography and corneal aberrations, which are able to be analyzed with the Eyestar. Then we will talk about the Mandala scan pattern, which we patented and which is inherent to the Eyestar. Then we will have more information about vision simulation in the Eyestar. We will do a practical guide to toric IOL planning with the Eyestar, and we will have users, clinicians speak about their first clinical experience with the Eyestar and its cataract suite. So please check out our website for more information, and you're certainly welcome to register for these upcoming webinars. With this, I'm already at the end of my short introduction, and I will now hand over to Thomas Beutler, who is Product Manager for Biometry. Let me quickly introduce Thomas Beutler to you. Thomas is with Haag-Streit for more than 16 years. He holds a degree in mechanical engineering, and over the years, he really deeply immersed himself into biometry and IOL calculation. In that function, he is in constant exchange with leading experts around the globe, and he was instrumental in the development of a number of products, most importantly, the Eyestar, and now over the years with the Eyestar. So Thomas is very well into the subject, and I'm pleased to hand over now to Thomas to give you more information about the Eyestar. So Thomas, please take over the screen.
Thank you very much, Reiner, for this nice introduction to the topic and myself. So I would also like to very much welcome all of you here for this webinar in the evening and on the first news on the Eyestar Precision OCT. For the next few minutes, I would like to share with you some basic information on the device, on the features and benefits, and on how it's going to proceed. So here we go. So we'll have the features of the device, we'll have benefits in the clinical application of it, some background also to it, because we do introduce quite some new features, as you've already heard with Reiner, and also from the video, where we have this patented scan pattern which we use. And last but not least, I'll also have a few words on live demonstration, which are available in these special times where lots of interaction with the customers has to be online instead of in person due to the limitations of Corona. So let's go a little bit more into detail and have a look at the features, benefits, and some technology things. First of all, the Eyestar Precision OCT is an all swept source optical coherence tomographer. So it's based on swept source technology. And now the question is, why did we choose swept source? There are other technologies available, but there are some special features of swept source technology that are beneficial in the application for cataract, but also for anterior segment surgery. If we want to visualize the eye entirely, we need high resolution, we need high speed, we need a long visualization range. So basically from the cornea to the retina, we want to see everything at once. And we want to have precision measurements. And this is one of the key parts, specifically in topography and the anterior chamber analysis, as well as for refractive purposes. So Swept Source OCT provides us with all this in one modality. We can have visualization of the anterior chamber of the eye in great detail. You see here some example images taken with the Cataract suite, which we are currently launching, of the Eyestar. On the left, we have 2 times phakic eye, what you see before cataract surgery, basically. On the right-hand side, on the top, we have once a pseudophakic patient, so an eye after the implantation of the IOL. And on the bottom right, we have, again, a phakic patient, so we have the crystalline lens still in place, but we do have an ICL, which is, in this case, iris mounted, iris clipped on, and it's also on display. So we have nice visualization of the entire anterior segment of the eye with all details. Now, when we want to do biometry from the cornea to the retina, we need a long scan range. And what you see here is not an image from the Cataract suite, but that's an image which we're going to provide you with the AC suite in the future. And you can see we have now the possibility to depict the entire eye. That's 18 millimeter diameter bead scan, which we see here from the cornea to the sclera. We see the anterior chamber, we see the chamber angle with the scleral spurs, and we also see the retina. And that's without stitching, one scan, and no combination of multiple modalities necessary. Then speed is also key in the whole game. Speed, first of all, improves the patient comfort. You all know how patients quickly are tiring. So the longer the event goes, the more tiring they get, the less cooperative a patient becomes. So speed is key to have the patient relaxed, to have the patient cooperative. And this again improves your measurement precision, your measurement quality. Speed also helps you to keep your technical staff happy. So the easier, the quicker the acquisition time is with a device, the more happy usually the technical staff also gets, because it makes life easier. And also in combination with the more relaxed patients, this is a win-win situation on both sides. And last but not least, when you have a high-speed data acquisition, you also have high precision, because all motion artifacts, which are always inherent when you look at human tissue, are minimal, and the compensation means are also reduced. Then, as I said before, one of the key features of the Eyestar is the precision measurement. We have precision measurements in optical biometry for the cataract application. So we have all eye biometry from the cornea, through the anterior chamber, through the lens, to the retina. Everything, one scan, one modality, no stitching. Then we have corneal topography of the front as well as the back surface. So we see the entire cornea, not only just the anterior section, but also the posterior section. And we also get information on the thickness of the cornea, on the entire structure. So we have pachymetry maps available throughout the entire cornea. All these features combined are pretty unique, and specifically with the fully automated measurement process, which we feature on the Eyestar, this helps to acquire quick and easy a data set, which will provide you with all the information necessary for cataract as well as refractive procedures. So that's why we've chosen Swept Source for speed, precision, comfort of the patient as well as of the user. So now how we do actually do those scans, how do we acquire the images? You've already heard in the video that we're using a patented scan pattern. We call this the Mandala scanning. So what's so unique about this and what's the difference as compared to standard technologies? What you see here on the left-hand side is a standard radial scan pattern. There, a line scan is rotated on the apex of the cornea and data is acquired. In the center, the data points are closer together. In the periphery, they are more far apart because it's a line which is rotated. It's also a scan pattern which is not continuous, so you always have interruptions at the end of every individual A scan. The Mandala scan pattern, on the other hand, which you see at the right-hand side, is a continuous scan pattern. It's a continuous combination of circular scans, which are always also going on the apex, but they have intersections with each other throughout the entire cornea. And that's what allows us to do OCT, inherent motion compensation. So with the Mandala scan pattern, we can compensate for eye motion without the need of an additional eye tracker, which is video-based or based on any other imaging means. So have a little bit more detailed look at it. Because of this circular pattern, we have a high density throughout the entire corneal surface. As said before, we have multiple intersections, not only on the apex, but also throughout the entire corneal surface. This allows OCT inherent motion compensation. We have the highest density again in the center. That's where all the visual effects are taking place. And we can now do a continuous scanning. And if you look at how scanners work best, they work best if you have a continuous pattern, if you don't have interrupts at edges or so. And this allows us then to provide also e-scans throughout the entire volumina acquired. So how do we do this in a complete workflow? We first do the scanning of the eye, then the cornea front is segmented. Based on this corneal front information, we can then do the motion compensation, and then from the motion compensated measurement cloud, we can do biometry from the cornea to the retina. We can do simulated keratometry, sim case. We can do topography, and topography in the quality of a type A topographer. And we can do B-scan imaging throughout the entire volumina. Now, a little bit more detail on the motion compensation. So we do the scans, and as we do the scans and we look at the image, we would see it like this. So we have on the left side the Mandala scan pattern as it's actually done on the eye, but you can see due to the motion, the eye image is blurred. It's distorted because the eye is moving all the time. That's what we have. It's also what you then see in the non-motion compensated OCT image on the bottom, that the whole thing is blurred out because of motion of the eye. Now, when we compensate for the motion, every single measurement point gets shifted according to the motion of the eye. And this helps us in two ways. First of all, the scan pattern gets denser, as you can see on the right-hand side, and we get rid of the motion artifacts. So now the image eye in the back is crystal clear, and also the B-scan underneath shows great details from the cornea to the retina. And this without the need of any additional eye tracker, which is based on another modality than OCT itself. The next feature I would like to talk about with you is the Swept Source based biometry, because here we have additional features which you can provide. We not only have an A scan, like with the old day biometers, where you have peaks of intensity of a signal from the cornea through the lens to the retina, but we have a full B scan of the entire eye. And I would like to show you how beneficial this may be. So with Swept Source OCT, the whole eye is depicted in one scan. So again, as said before, no need for stitching, no need for combination of different sections of the eye. It's in one shot. So every A scan goes from the cornea to the retina. This allows to have highest precision throughout the entire scan. We then provide the A scans, as you know it from other biometers, with the intensity plots, the little mountain plots, cornea, lens, retina. But in addition, you also get B scans, and a set of 16 B scans is what's part of the cataract suite. So you see the entire anterior chamber and also the rest to the retina in great detail. You can rotate 16 B scans and look at anatomical details. Also, you can screen for anomalies which you might have missed if you just have had an A scan. So let's have a look at an example. Here we see a pseudophakic eye with just the A scan. If we look at it, we see here the front. So basically, here we have the cornea. Here we have the lens. But in the lens, something is a little bit weird, because we have one peak here, one peak here, one peak here. That's weird, because if you have pseudophakic eye, you would only look for 2 peaks, not 3. So something seems to be weird in this patient. And we have back here the retinal peak that looks quite normal. We have the ILM interface in the limiting membrane, and the retinal pigment epithelium, which is the highest peak back there. So actually, what happened here? So if we now have, in addition to the A scan, a full B scan, we see what happens, because now we see, again, the cornea, we see the lens, and we see that the posterior capsular bag here is actually a little bit lifted from the back surface of the IOL. So there seems to be liquid trapped behind the IOL. And if we have now the combination of the A and B scan, we see how these are aligned and how these also are combined well. So we see cornea, we see the IOL, we see the posterior capsular bag, which is a little bit lifted, and we see the retina. So now we have a real answer to the patient why, for example, in this case, his optical result was not perfect. Due to the trapped liquid, the IOL was shifted a little bit forward, so the lens position was not perfect, and therefore his visual acuity was not perfect in the end. What then was done, they basically removed the liquid behind the lens shifted in its perfect position, and everything was fine. And that's a good example how the B scan can improve your clinical judgment on a patient, and then also improves your interaction with the patient to get him happy. The next feature I would like to talk about with you is the dual zone reflective keratometry, which we are featuring on the Eyestar as well. You might wonder, well, Thomas just told us he's getting SIMCase. Why do they also do reflective keratometry that is tear film dependent? Well, let's have a look at this. So what are the benefits of dual zone reflective keratometry? First of all, it's a well-proven and well-established measurement mean. We first introduced this more than a decade ago on the Eyestar with 2 × 16 LED points on the cornea. It has shown its superiority to just 6-point-based reflective keratometry to provide improved outcomes on toric IOLs, and it's working with standard IOL constants. So there's no need to adapt any IOL constants if you use same keratometry as with standard devices. What we did to improve the whole game again is we shifted the second circle by half the spacing to have an improved resolution again on the angle. And we introduced telecentric optics with the Eyestar. So we have now a distance-independent measurement of the keratometry. And as I said before, standard keratometry, reflective keratometry, can be used with standard IOL calculation formulae, standard A constants. So the 32 markers are spread like with the Eyestar on 1.65 millimeters and 2.3 millimeter optical zone. They provide stable and very reproducible K readings. And the measurements are matched to the IR image, which is on display here. That's the measurement image, as well as on a high resolution color image of the eye. So this could basically be used then as baseline information on other applications like surgical navigations or also on femtosecond laser, for example. So now again, why reflective keratometry and not just SIMCase from topography? The answer is simple. The two measurements are inherently different. The keratometry from reflections is a fit of a geometrical body of an ellipsoid to the reflections on the cornea. So we look at the shape immediately, and we have the keratometry inherent steep and flat meridian concept in the basic body which we shape to the reflections. The SIMCase, they're based on elevation data. So we look at height curves first, which we get from the OCT, and then we derive from there a simulation on what keratometry could look like at a certain diameter. Now, you can make sure that in average, the two modalities provide the same results. That's also what we did with the Eyestar. But on the individual patient, you will realize that they may have quite large variations. And therefore, I'd like to show you a quick outtake of our clinical study, which we use for registration purposes. On the top line, you have the plots for the comparison Eyestar reflective keratometry to Eyestar, which only has reflective keratometry. And on the bottom, you have the Eyestar SIMK versus the Eyestar reflective keratometry. Now, the right boxes, they show you we have a nice correlation. They're basically equal in average, but the left box, the blunt ultimate plots, they show you that the variability between individual measurements is by far bigger for the comparison SIMCase to reflective keratometry as compared to reflective keratometry against reflective keratometry. So if you want to have the best precision, you would like to have reflective keratometry. And as we all know, in cataract surgery, the K readings are one of the most important measurements apart from the axial length to get good outcomes. And that's why we've chosen to add reflective keratometry to the Eyestar as just to use SIMCase. The next feature I'd like to show you is the Swept Source OCT-based topography. So everything we look at now is based on OCT only. So it's all OCT data-based, and therefore we don't have all the issues of reflective technologies. like you know better than I do, at least, from your clinical practice. What we get from the Swept Source OCT-based topography is we get a type A precision from the topography. So we are in compliance with the ISO 19980 standard, and we provide the respective accuracy and reproducibility for type A corneal topographer. We get corneal topography of the front and the back surface, and we get pachymetry. In the Cataract suite, which we are launching right now, we have excellent topography maps for the corneal power. We have axial maps, we have tangential maps, we have elevation maps. We also have irregularity maps with a ellipsoid base body. We provide this with an optical diameter of 7.5 millimeters. Larger maps are going to be part of the AC suite, which we're going to release later with the Eyestar. And we also have full resolution pachymetry map throughout the 7.5 millimeter optical zone available in the Cataract suite. We also do Zernike analysis with the data. We do vision simulation, and we do a zone-based keratometry. So what is the advantage of these three modalities? If you have the Zernike analysis, you can basically see what visual effect comes from what kind of imperfeciency of the cornea. So you can see coma, you can see sphericity. I'm sorry about that. It's always a word I'm stumbling on. Sphericity. You can see against the rule, with the rule, astigmatism. You can see trefoil. Everything is there at hand for you. And it also helps you to judge, is a particular patient a candidate for a premium IOL, or do I better go for other solutions? Then the vision simulation tool allows you to transfer this rather theoretical data for a patient into something he can work with, into something that shows him how his eye would work, how his vision would be. So we have the letter E, we also have the Lambolt rings available that show the distortion from the imperfect cornea. And the zone-based keratometry lets you also have an improved information on the regularity of an astigmatism, for example. So you see if everything is nicely throughout the entire cornea, from the central 3 to the intermediate 5 to the peripheral 7 millimeter zone. That's all there for the implantation. Now have a look again at one example here. So we have a pretty standard patient, an eye length of 23.06 millimeters, normal anterior chamber depth, 3.2 millimeters about. The cornea, yeah, rather thin, but still okay. It's a non-altered cornea, so that's not a post-LASIK patient. If you think, oh, that's a thin cornea, no, it's a normal cornea here. And we have astigmatism of 1.5 diopters and average K readings of 43.5 diopters. So pretty standard, but it might be a good candidate for a low power toric because we do have quite some astigmatism already there. If we just have biometry with this data, that's what we have to go for. And we have a little bit of a gambling. Is this astigmatism regular? Is it symmetrical? Are there any asymmetries? We just don't know because keratometry cannot provide this information. Keratometry is blind for irregularities of the cornea. Now, if we add topography, and that's the topography of this particular patient, we can already see, that's not a perfect astigmatism. We see that the top and the bottom lobes are a little bit bent. The central zone looks still quite okay, but at least if we go to the periphery, there's quite some bending. So if you look at it, I introduced here a circular line for 5 millimeters. So that's basically the optics of an IOL. And we see that the whole thing is still a little bit bent, but not too much. So we see, if this patient insists on a toric, we might have to talk. Now, we can have a further look. we can now have a look at the zone-based keratometry, because this again reveals quite some good information in this particular case here. So if we look at the central 3 millimeter, that's basically a day vision state, we see that the keratometry model still is quite valid. It's almost 90 degrees to each other, the steep and the flat meridians, and they're almost in line. So there might be a good chance that at least for day vision, a toric could help. We see on the intermediate and on the peripheral zones that there the asymmetry is prominent, and therefore only a steep and the flat axis are on display and not two steep and two flat ones, because there's basically just a steep and flat area. Okay, so again, the additional information we get from the zone-based keratometry helps us to judge how do we proceed with this particular patient if he or she is asking for a toric. Again, we have the same outcome as if we just look at the topography itself, but with more details and with more numbers. And last but not least, we should have a look at the Zernike decompensation. So basically at the split up of the visual effects. So what is Zernike? With Zernike, we can split up the visual effects of the cornea into different components. So we see tilt, we see astigmatism, we see defocus. And the top three are basically our lower order aberrations. Those we can compensate with glasses or an IOL. And then everything below this line is then called higher order aberrations. And this we cannot compensate necessarily with an IOL, but we would need different means. Still, we are very much interested into this because it shows us nicely asymmetry, like with the coma. And we also see the spherical aberration there. So if we have an aspheric IOL, we can check if this would match with the asphericity of the cornea and if this would actually help to compensate for this. Here we have a quick look how these different means are having an effect on the visual acuity of the patient. We have here Landolt ring simulations, and we see that the defocus basically is the blur we get from myopia or hyperopia. We see that the astigmatism is distorting our image. We see that coma leads to multiple images. So we have not only a C, but we have several Cs in vertical or horizontal orientation. So it really helps us to show the patient what's happening with his visual acuity. So let's go back to the example, which we did look at it. That's the display of the Eyestar. On the left, you have all the different coefficients. You have the top three ones, which are our lower order aberrations. We have then the bottom ones up to the fourth order in the Cataract suite, which are the higher order aberrations. Now we have here in this particular example chosen a 6 millimeter pupil. So let's say that would be night vision, for example. So if we look at this, we see we have quite some distortion. Now, if we take away all the lower order aberrations, we can show the patient what the effect would be if we implant a toric IOL that fits perfect to his astigmatism. So we go there and we see now, oops, sorry, that was one slide too much, that if we put in a toric IOL, for example, we could get rid of some of the effect, but we still have some distortion. And this is because of the non-perfect astigmatism. We see here that we have some coma, so some asymmetry, which is on display in Zernike polynomials. Now, if we say, let's have a look how this would look at day vision, we simply go and change the diameter we look at here from 6 to, for example, 3 millimeter. And that's what we would get there. So at day vision, still I just unticked the lower order aberration, so what I can correct with an IOL. And we see that now at day, a toric could lead to quite an improvement in his vision. At night, there is some remaining effect still there. So that's what we see here, this can easily be used in the communication with the patient. So we see on the left, that's without correction. That's with a toric at night. That's with a toric at day. This helps you also to then go and maybe do an upsale of a patient that might have gone just for a standard spherical IOL instead of a premium implant. So this feature helps you in the communication with the patient, helps them to get the right decision on the implant itself. Okay. So as a summary, we have a 7.5 millimeter topography, type A, standard topography. We have zone-based keratometry for an additional judgment, how we can proceed with toric IOLs. And we have the Zernike analysis and the vision simulation for the communication with the patient and the improvement of the clinical decision process. The next feature I'd like to talk a little bit is the lens tilt feature. So with the imaging means provided by Swept Source OCT, we can now have a detailed look at the lens of the patient, not only the crystalline, but also on the implanted IOL. So we can identify the plane of the maximum lens tilt to the patient's visual axis. And this is a good parameter if you want to go for premium IOLs, because if you have extensive lens tilt, we all know, then we would rather go for a standard IOL than a premium to make sure that we don't have side effects because of the tilting. We display the B scan of the maximum tilt. We display also where this maximum tilt is in the upfront image of the eye. And you can see the decentration of the lens and also of an implant as compared to the apex on the cornea. When we look at a little bit more detail, we see here 2 examples of lens tilt analysis. The top one is a standard phakic patient. The bottom one is a pseudo-phakic patient. It's not the same patients. They are images from different patients. You might see, well, it's both from the left-hand side, and one looks tilted to one side, the other to the other side. They are both tilted to the same side, but you can see that the OCT cut is once from temporal to nasal. That's the top image, and then the bottom image is from nasal to temporal. That's why we have the little dot at the beginning of the line that always shows from where does it start, and it's also combined with the dot in the B scan. So you always know what you're looking at. So here we have now additional information to see, might this patient be a good candidate for a premium implant? And also if you have some refractive surprises postoperatively, and you would see extensive lens tilt in the B scan here, you can also then explain why the vision might not be perfect. Then, last but not least, the fully automated measurement process. Let's talk a little bit about this. So we can acquire all this data with one single measurement. And for both eyes, the measurement from the time the patient goes into the headrest till he's released, it's below 40 seconds. So it's almost nothing. The device moves itself internally, so there's no external motion there. So the patient is always safe, feels relaxed. It's easy to delegate, so independently of the skills of the technical staff using the device, you always get the same quality. And the patient compliance improves because the whole thing is so quick. Below 1 minute, everything is done. Then another advantage of the Eyestar is that the user interface can be switched from the patient's view from the right-hand side to the back or to the left side even. This helps us to accommodate needs of your space restrictions. If you have, for example, a room where you don't have the space to be at the side of the device, we can move the screen on the back side, or we can move it on the opposite side again. We also provide a table to the unit, height adjustable table with a little support for a keyboard and a mouse if you want to use keyboard and mouse. If you combine it with your EMR system, you might not even have a need for keyboard and mouse. But if yes, then you can also have this on the table itself. It's slim design, it's space saving, and fits any room. Okay, so let's have a little summary what we've just seen. So we have the Eyestar Precision OCT. With the Cataract suite, we provide a perfect solution for the ambitious cataract surgeon to fulfill all his needs for standard spherical IOLs, to torics, to multifocals, and also combinations of it, to always get the optimum patient comfort, patient outcome, also at the best level, and patient satisfaction, which is most important. That's about the features and benefit of the unit itself. Next thing I would like to talk to you just quickly is the possibility to have live demonstrations. You've seen this is an all-in-one device. Everything is in the device itself. So it's also possible to demonstrate the device online quite easily. And we did it already in the past several times. We did demonstrations with some Haag-Streit representatives throughout Europe already. Usually that's a 60-minute webinar, which is first agreed on in combination with your local representative. And then you have a combination of product presentations like we do here. We'll have a hands-on session where you can see the device. You see here myself and Marcus, a friend of ours here at the Haag-Streit office. And he's the patient. I was the doctor. We did show an exam. We did go through the analysis on the unit itself. You see there's no fake. You can see the screen. You can see the screen in the video as well as live. Everything is there. For the moment, our capabilities are a little bit limited because we have the units just in-house here in Königs. But as we go on and we deliver first demonstration units also to our representative throughout Europe, the capabilities to have those online demos will increase. So basically ask your representative if this is already available, and then we'll see and have a look at it. And just to give you a little flavor how this could look like, that's a presentation I did a few days ago, and basically just let you enjoy it. I just realized that I forgot to also provide you with the audio on the video itself. So basically I'm going to do the comment myself here. So we see the acquisition itself. We do the setup on the eye status here, and then we go on. So I click on the eye status. You can see that the screen on the right-hand side and also in the device is always switching as I go on. Now the patient can move forward and grab on the handles to get more stability. That's with elder patients always very useful. And then I click on next to start the acquisition, basically. And from this time till we have the acquisition, it's below 40 seconds. So we see now on the left-hand top side, the first image acquisition. You might have realized that the central point, which is the fixation target, changed from green to red. That's also what the patient can see. So if the patient target is switched from green to red, that means that the acquisition, actually the measurement is starting, and you can advise the patient to blink at just the time when the target switches from green to red to get easiest and most precise measurements acquired. And as you can see, the patient can relax already. The data is there. We also have immediate feedback on the bottom about the quality. We have these smiling faces. On the topography, that's the OCT information. And on keratometry, that's the reflection-based keratometry, which we have. So we have immediate feedback. Is everything okay? Or was there something unusual? Also throughout the measurement, you get immediate feedback. If the patient should open his eye wider to get the full coverage, that's feedback you can get. On the complete overview result, you have on the top left and the top right for the left and the right eye, the topography maps. You have the B scans throughout the anterior chamber. You have the keratometry, the axial length, everything at hand at once. And if you click on any of these individual measurements, you get then more details as you go. But that will be then part of the entire online demonstration there. And this would be a little bit too much. You've seen some of the details already in my presentation here. But if you want to know more, then we will go for an online presentation in more detail. So that's basically it. Thank you very much for your attention, and we can go now to the Q&A session.
So Thomas, I think we were quite clear. There is no
either we have been quite clear or it was too complicated.
If there is no questions, I think we should not be any longer here. I would like to take the opportunity to thank all the participants for their participation. I really hope you share now a little bit of our enthusiasm for this new precision OCT device. If you have wish for more information, please contact us or our distributors. We are already there. As Thomas said, we can also do online these demonstrations of the device. And yes, I hope to see you around in one of our webinars that we have with leading experts or with clinicians in the next seminars of this biometry focus months. Or certainly, I would like to see you in person again at one of the congresses that might be coming up in fall or in any other occasions. Thank you very much for your valued participation and have a nice evening. Thanks a lot. Bye-bye.